Hello students. So today we will study classification and periodicity of elements theory part 1. Disclaimer: the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So, what are the topics that we are going to study today? First of all, we will list some early attempts that were made to classify the elements, then the modern periodic law and present form of periodic table, classification of elements, periodic trends in properties of elements, and then we will sum up with a summary. So, let us first see what are the early attempts that were made to classify the elements. So, basically, elements were made to classify so that their study can be easier, right? So we can study the physical properties and chemical properties in a much more convenient way, because there are many elements, and if we try to just study each of them individually, that would be a pain to us. Okay, so for that reason what we did is we classified the elements in groups, and those groups will have the same type of property. So many scientists have attempted that, and let us see the names of those. First was our Proud's hypothesis. Second was of Daubernian triads. Then Newland's law of octaves. Lothar Mayer's atomic volume curve, and Mendeleev's periodic law in 1869. So this was the last, attempt before the modern periodic table. Then at last, what they did is they developed the modern periodic table that we see today. The properties of elements are periodic function of their atomic weights and periodic law. And modern periodic law, okay. So let us look at the modern periodic law and present form of the periodic table. So the basis of the modern periodic law was given by Henry Moseley, and he shows that the atomic number is a fundamental property of any element, then its atomic mass, and formulated the modern periodic law. So what do you mean by this? So Sir Dmitry Mendeleev, what he did, he also classified the element, but in his classification, he took the atomic weight as the atomic mass as the fundamental property, and that was the mistake he was making. Okay, so Henry Moseley, rather than taking up the atomic mass, he took the atomic number, and that turned out to be a genius piece of idea, and with the help of that he formulated the modern periodic law. So modern periodic law can be stated as what? So you can see here the statement is given. The statement says that the physical and chemical properties, okay, the physical and chemical properties of the element, so the physical and chemical properties of the elements are what? They are the periodic function of the atomic number. Okay, so you can think it in this way, that as we are changing the atomic number, the the physical and chemical properties are changing accordingly. So it's a function of the atomic number. Clear? This modern periodic table is also called as Bohr's periodic table, and it is just graphical representation of the Aufbau principle. So Aufbau principle, what was Aufbau principle? So it was basically the filling of your atomic orbital on the basis of energy. Clear? Now in this table, what he did, he arranged your elements in the increasing order of atomic number, and those were the form with the help of which he formulated the modern periodic table. Now that the drawback of the Dmitry Mendeleev periodic table was that he could not address the isotopes, because isotopes have the same atomic number but different atomic mass, and since his table was based upon your atomic weight, so two isotopes would have been considered as different elements, but this was not the case. They were much more closer in the physical and chemical properties, and they cannot be distinguished also, right? So due to that reason, his table was facing difficulty. So when we do the same classification on the basis of atomic number, the problem of isotopes are removed. Why? Because now isotopes can be considered as in the one square or in the one bracket, right? So because both the elements would have the same atomic number, both the isotopes will have the same atomic number but different atomic weight, right? Clear? So same thing is written here. The isotopes, they are grouped together as they have the same atomic number. Now let us talk about the characteristics of the table. So there are 7 periods and 18 groups. So we'll look upon this when the image is given on the next part. So we'll look upon this. What do you mean by periods and what do you mean by groups? And the concept of subgroups A and B is removed, and the group are numbered from 1 to 18. So initially there was the use of A and B, so they were called as groups and subgroups. But later on, this concept was removed and simple numbering was done from 1 to 18. The name of 0 group is changed to group 18 now. Clear? So we'll look what it is this 0 group where it changed to group 18. So this is the modern periodic table. Now both types of we can say naming is given here. So this was the old one. So we started from 1A, going from 2A, then 3A, 4A, 5A, 6A, 7A, and then 8 is this. And after this B has started. So 2B, 3B, and it goes up to what? It goes up to your 0 group. Clear? So you can see here this was the old trend. So they started from 1A, 2A, 3A, 4A, 5A, 6A, 7A. Then 8 was having 3 groups. Okay. Then again 1B, 2B, 3B, 4B, 5B, 6B, 7B. And at last what they did is they named the last group as 0. Clear? Now this was the old way to do it. So okay. Now what was the new way? The new way was that he numbered it like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. As simple as that, right? So there was now no confusion of groups and subgroups. So there are total of how many groups? You can see very clearly. There are total of 18 groups, right? Total of 18 groups. Then what about the periods? You can see here there are 7 periods. 1, 2, 3, 4, 5, 6, and 7. These two groups that are these two lines that are given in the bottom, they are not of separate period but of the period that is here. Okay, so this series here, this upper series, this is of 6th group, and this lower series, this is of the 7th group. Okay, so this is our overall modern periodic law. Here we have the S block. Now there was further classification. So this is the S block, right? So sometimes you will see hydrogen here, sometimes you will see so hydrogen has a you can say an orthodox position. So it cannot be classified rather in the S block nor in the P block. Okay, so these are some characteristics of metal, some characteristics of non-metal. So that is the reason there is a confusion for that. Other than that, all the positions are fixed. Now the first two groups, this group and this group, this is under the S block. Okay, and starting from 13 and moving on to 18, this is of P block. Clear? And in between we have from 3 to 12. So here we have 3 to 12. This is of D block. And in the bottom side, the two lines which I mentioned earlier, these are of F block. These are what? These are F block elements. Clear? So again I am summarizing this. So there are two groups initially. They are they are of S block. At the end we have from 13 to 18, this is of P block. From 3 to 12, it is of D block. And the two lines in the bottoms are of F block. Now let us see it again in the theoretical form. So we have seen it in the table. So how you will identify a element seeing its electronic configuration, that which group it belongs. So we will see that. So first of all, for the S block element, for the S block element, I said that there are two group 1 and group 2. Okay. Now group 1 is also called as alkali metals, whereas group 2 are also called as alkaline earth metals. Now what is the electronic configuration that differs it from the other? So the difference is that their last electrons in the case of the neutral state lies in the s orbital. Okay, what do you mean by this again? So they are saying that the last electron which you are filling in the case of neutral element, this should go in the s orbital. So such elements were placed under the s block. Now we can write the general configuration accordingly. So since we are going for the last s block element, so we can write the general configuration as ns1 to 2, means that valence configuration is n is the principal quantum number, s is your orbital, and there can be 1 or 2 electrons depending upon the position in the periodic table. Clear? Okay. Now next is the p block element. Now we have said it earlier that which are the groups that will belong to p block elements. So for that we will go from 13 to 18. So all elements that are falling in from group in the group 13 to 18, they are in the p block element except helium. Okay, so excluding helium, all of the elements that are in the 13 to 18 belongs to this block. Now their last electron enters in p block, so this is the reason they are called as p block element, and this is the reason we are excluding helium. So if you remember the electronic configuration of helium, it is simply 1s2. Now its last electron is going to the s orbital and not to the p orbital. For that reason it is not under the p block. Again, what will be the general configuration? So the general electronic configuration will be ns2 and np1 to 6. So why are we writing it n here? So because this means the s orbital is completely filled in the valence shell, and the valence shell principal quantum number is used for the p also. So therefore ns2 np1 to 6. Clear? So this is our valence electronic configuration. Now s block and p block are also known as representative elements. So this terminology is very important because it may be used sometime and you may get confused that what are they talking about, right? So you should be well aware about this, that your s and p block elements are also called representative elements or main group element, right? So if you are somewhat into this periodic table, or if you have studied this periodic table, then you have must have heard this term main group element. So by main group element, we mean that all the s block element and p block element fall under this group. Clear? Now next we will talk about diagonal relationship. So what is diagonal relationship? So according to diagonal relationship, the first member of each group of s and p block element show different characteristics from the rest of the member of the group. So what do you mean by this? At the first member, so if you look at the s block, okay, then the first element will show different characteristics. Similar goes for the p block. Okay, so suppose we are saying that, okay, what is the first element of s block? So hydrogen, helium, lithium. Okay, so lithium is the first element. So lithium, so we don't take here hydrogen. I mentioned it earlier also, I'm mentioning it now also, that hydrogen's position is not fixed. So we start with the lithium. So this is the first element in the say your alkali metal. Okay, so this will show properties that will not be in accordance with the rest of the element that are present in the group. Okay, then after lithium, hydrogen, helium, then lithium, then we have beryllium. So same goes for beryllium, boron, same goes for boron, carbon. So they all of them show different characteristics from the rest of the members of the same group. But however, the three element of second period, lithium, beryllium, boron, shows diagonal similarity with elements. So what do we mean by this? So they are saying that although they don't show the similarity in their characteristics with the rest of the group, but they do show similarity with the diagonal element. So if you look at the periodic table, okay, just take a diagonal line, and wherever the next consecutive element comes, you will say that that is the diagonal element with respect to our lithium, beryllium, and boron. Okay, on the right hand side, not on the left hand side, on the right hand side of the third period, you will find it. Okay, so these three elements, that is lithium, beryllium, and boron, they show property similarity with magnesium, aluminum, and silicon, respectively. Okay, so lithium shows similarity with magnesium, beryllium shows similarity with aluminium, and boron shows similarity with the silicon. And this is called as diagonal relationship. So this is very, very important for your exams. So this is the second period, and this is the third period, right? So this is the second period, and this is the third period. So suppose lithium is here, so it will not show similarity with the elements just below it. It will go on to the next element, so it will show similarity with magnesium. Similarly, beryllium will show similarity with aluminium, and boron will show similarity with silicon. So you should remember this, right? So that it helps in predicting your physical and chemical properties. So lithium and magnesium have similar properties, beryllium and aluminium have similar properties, and boron and silicon have similar properties. Next, we will talk about D block or transition elements. So D block also has a different name, similar like we have main group for S and P block. D block has a separate name. So all the elements which are in from group 3 to 12, okay, from group 3 to 12 in the periodic table, they all belong to the D block element, and their last electron enters in the D block. So again, as we have seen it earlier also, that for S block, last electron should go to the S orbital. For P block, last electron should go to the P orbital. Similarly, for D block, the last electron should go to the D orbital. Clear? Now, two outermost shells of D block elements are incomplete. Okay. So what is it said there? That the two outermost shells of the D block elements are incomplete. Now we will see what is the general electronic configuration of D block element. So this is very important to remember. So for say your S block element, it is NS 1 to 2. For P block elements, it is NP, NS, NS2, NP 1 to 6. And for our D block element, it is N minus 1, D 1 to 10, and NS 0 to 2. Okay, so this is the case. So what am I saying again? That the electronic configuration is N minus 1, D 1 to 10, and NS 0 to 2. Now what should be remembered here is that although your electron is going, or the outermost electron seems to be NS, but the last electron goes to the one inner shell, and it is N minus 1, D 1 to 10. So initially S block and P block, we are taking the same number, that is NS and NP, but in this case we are taking the N minus 1. Clear? Okay. Now there can be a case that S orbital has no electron and it may directly go to the D orbital. So that can be the case also. So this should also be considered. Now talking about the last block, that is the F block or the inner transition element. So F block are called what? They are called as inner transition elements. What is the general configuration? Again, remember this is very important. So it is NS2, N minus 1, D 0 1 to 10, okay, and N minus 2, F 1 to 14. And here also the last electron enters in the F orbital. As similar like S for S, P and D, we follow the same trend here also. Now, keeping this in mind, there are two series. So they are called lengthenoids and actinoids. So if your last electron is going to the 4F orbital, then we call them as lengthenoid, and if it is going to the 5F, then we call it as actinoids, and they are also called as rare earth elements. Now here is a very important part of nomenclature. So although we have not included nomenclature for the elements, but you will find that the elements which have atomic number greater than 100, they do have a nomenclature. So what is that nomenclature? So their name are derived in 3 digits, right? So because they are the elements that are found after the group after the number 100. So of course their atomic number will have 3 digits, right? And for each digit we have a code, and at last we put this suffix which is em, and that completes the name of the elements that are after 100. Okay, they are having of which they are having atomic number greater than 100. Okay, clear? So what are the roots for each of this number, or each of this digit? So for say 1 we have nil, for 2 we have un, for 3 we have by, 4 we have try, 5 we have quad, 6 we have pent, 7 we have hex. Okay, sorry for the mistake. So I was taking this one. So we are going with this. Okay, so 0 nil, 1 we have un, 2 we have by, 3 we have try, 4 we have quad, 5 we have pent, 6 we have hex, 7 we have sept, 8 we have oct, and 9 we have n. Okay, so this is the thing. This is the serial number. Again, so this is the say your what? This is your root name. So suppose if in any element, if it is, suppose say we are taking any element, like we have taken 101 atomic number, right? So for what is the root for 1? So you will go to the table, refer to the table. It is easy to learn also, very easy to learn. So for 1, what we have the root? We have the root as un. Okay, so we put un here. Very good, very good. Then for 0, what we have? For 0 we have nil, so we put nil here. Again we have 1, so we again put un here. And at last I have said that you have to add suffix, that is em. So un, nil, unneum. So this will be the name for 101. Now you can take different examples in which the atomic number will be including 3 digits. Okay, of course we don't have elements greater than that require your number that is greater than 3 digits. So we will take such elements, and you should try this to number them. Okay, you should try to number them. It's a good practice for you. Now we will talk about the trends. So earlier when we were starting the theory part, we said that we are just classifying them in groups or periods so that their properties analysis become easy, right? So for that we have trends, so that their physical or chemical properties can be easily studied, right, for the large number of elements. So all of these elements display several other trends. We can use the periodic law and periodic formation of to predict the physical and chemical properties. So what we are doing here is we are using that table that we have seen right now, long form of modern periodic table, and using that table we will be able to say predict the physical, chemical, and atomic properties up to a very greater extent, and that will quite surprise you, right? It is quite surprising to say predict the properties, right? Because it is like you are just saying that okay, this is the element with this atomic number, and without experimenting or without doing any calculation, you are approximately able to say or predict its atomic number, like it's no, it's not its atomic number, but its physical properties, if boiling point or something like that, then its chemical properties, that what type of nitrites it will form, what type of oxides it will form. So this is quite very fascinating, right? So just think about it. So let us now see some of the physical and chemical properties to encourage, so that we can appreciate the classification. Okay, so we will see the physical and chemical properties. First is atomic radius. Okay, it's very simple. By looking at this term, you must have understand what we are talking about. So we are talking about the radius of atom. Now there are various ways to define this atomic radius. We will see to it. So what is atomic radius in general? If you want an idea, so it is simply defined as a distance from the center. So we are defining the distance from the center of the nucleus to the outermost shell containing electrons. Okay. Now it can be referred for both covalent and metallic radius. Okay, so because an atom can be covalently bonded also, and there are atoms which are say having metallic bonds also. For both of them we will have some radii, and that will depend upon whether the element is non-metal or metal. So if it is a metal, it will form the metallic type of structure, and if it is a non-metal, it will form a covalent bond, right? And accordingly we will calculate covalent radius for non-metal and metallic radius for metal. Now on moving left to right in a period, we will find that atomic radii decreases, and when we move down the group, the atomic radii increases. So why is it happening? Because when we are moving from left to right, we are adding electrons in the same shell. Okay, so now if initially there were 2 electrons, now there are 3 electrons, and hence the overall force on that your shell also increases because of the number of electrons have increased, and for each electron you are adding some force, right? Okay, so this is the reason they are now pulled inwards, and this atomic radii decreases. Clear? Now what are the 3 types of atomic radii? So first is covalent radius. What are covalent radius? What is covalent radius? So suppose we have a diatomic molecule, say AA. So we are taking the imaginary case, a diatomic molecule we are considering, and that is having the formula A2. So we can write it in this way also, A bond A. Therefore, what will be the radius? So covalent radius will be simply the distance between the nucleus of these two A's divided by 2. This will give you what? This will give you the what? This will give you the covalent radius. So what is DAA here? So I have told you earlier. So it is the bond length or the distance between two covalently bonded atoms. Now what about heterodiatomic molecule? Suppose we are taking a heterodiatomic molecule, means both the atoms are different. One is A and another one is B. Now where A and B are having very small difference in their electronegativity. So this is also very, very important, that chi A minus chi B should be very, very small, or it will be difficult to do so. Because see, if chi A minus chi B is very large, that means one is metal, non-metal. In that case, and if there is much more, say, your difference, then there can be case of formation of ionic bond also, and we are defining covalent radius. So for that reason, what we are doing is we are taking 2 elements such that the difference in their electronegativity is small. What will be the bond length? So it will be simply represented by DA bond B. Okay, so this is the bond distance of the between the 2 atoms. So we can write it as what? We can write it as the summation of the individual radii of A and B. So RA plus RB will give you the bond length or the bond distance. So again, same thing is mentioned here. This is covalent radii of A and B respectively. And chi A, chi B, so we know, you know also, we have mentioned it also, that chi A is the electronegativity of A and chi B is the electronegativity of B respectively. Clear? Okay. So what will happen when chi A and chi A minus chi B is considerable? It is not small. Then in that case, DAB is not simply RA plus RB. So this is very, very important. So initially we have seen that for normal case where chi A, chi B is very, very small, we have simply added the 2 radii, ARA and RB, and we have calculated DAB. But in case chi A minus chi B is considerably large, then what we will do? Then the distance between these two is not simply RA plus RB, because there is a case of overlap and much more phenomena going underneath. So we have RA plus RB minus 0.09 multiplied by IA minus chi B. So due to the say greater attraction, because the electronegativity difference is large, so they will be attracted very strongly. As a result of it, you will see that what you will see that your RA plus RB is being not the actual case. It is not equal to DAB. It is less than DAB. Sorry, it is greater than DAB. For that reason, what we do, we subtract a small amount, which is 0.09 chi A minus chi B. Clear? Now let us talk about the metallic radius. So of course, your metallic radius will be defined for the metals. So it is simply R dash can be defined as, or your metallic radius can be defined as D by 2. Where R dash is what? R dash is the actual size of atom. Okay. And what is D? D is the adjacent distance between distance between the adjacent metal ions in the metallic lattice. So you take a metallic lattice, and the distance between two adjacent metal ions is called as the what? Is called as your D. So if you divide this by 2, then we get our metallic radius, that is R dash. Third, we will talk about van der Waals radius. What is van der Waals radius? So here also we have divided the D by 2, but this D is different with respect to your metallic one and with respect to your covalent one. So let us see what this D is first. So this is the distance between the nuclei of two identical non-bonded isolated atoms. What do you mean by this? So this thing is very important to understand, that what is van der Waals radii actually. So for this you have to consider two molecules, right? Now there are suppose two molecules, and those two molecules are homoatomic first of all and identical. Suppose you are taking nitrogen, so you are taking two molecules of nitrogen, that is N2. Now you will consider the closest approach. What is closest approach? Means the distance, the minimum distance that can be reduced between these two, okay, without any external aid. So what is the closest distance they can come? Okay, clear? Now you will measure the distance between the two atoms, okay, and that will be divided by 2 to give you the van der Waals radius. So it is basically, you can say, the distance between two atoms of different molecules, okay, distance between the two atomic nuclei of the different molecule, and that is the minimum distance you are considering. Then you divide it by 2 and you get the van der Waals radius. So R1 is much more greater than the actual size of atom. Why is it written so? You should understand this. So see, what we have done is we have taken the overall molecule. Now the overall molecule is having a greater area of, say, you can say greater effective area than the actual atom, right? Now this same goes for the other one, with the your other molecule. Now adding these two will make a scenario where your radius that you have calculated is much more greater than the actual size, because of the overall area the molecule has occupied. Clear? This is the trend that is very, very important. This should be remembered always, that your van der Waals radii is greater than the metallic radii, which is in turn greater than the covalent radii. So why is van der Waals radii we have discussed, why it is large we have discussed. What about metallic radii? Why is it so large than the covalent radii? Because metallic radii is for metals, and metals do not overlap, right? They do not form covalent bond to overlap. So when there is no overlap, no area is in common right now. Due to that reason, there is no subtraction of the radius, right? But in case of covalent radii, there is overlap, and that results in some common area between these two atoms, and as a result we have to subtract that area, right? And that is the reason that is the smallest one. Now at the end of the period, atomic radii of inert gas are exceptionally large because they do not form molecule, and their radii are simply van der Waals radii. So this is also important. So you know it very well that inert gases are what? They have complete valence shell, or you can say they have complete octet. Due to that reason, they do not form, like say if you have helium, they do not form He2 or Xe2, and as a result of that, they are existing individually. Clear? And therefore they do not form molecules, so they are exceptionally large, and hence their radii are simple van der Waals radii. Clear? Okay, let us see the trend in the periodic table of atomic radii. Before that, we will look upon the ionic radii. So the distance of the outermost shell of an ion from its nucleus is called as ionic radii. Very obvious to understand. So what are we considering now? We are considering ions. So now the distance between the outermost shell and the nuclei is considered as ionic radii. Now cationic radii is always smaller than its neutral atom. Okay, whereas while an ionic radii is always greater than its neutral atom. Okay, so if you are considering your cation, then it will be always smaller than the neutral atom. Why is it so? Because we have removed one electron And as a result of that removal, what will happen is that your say your force on per electron will increase because the proton number is same but the electron number is reduced. So due to this, a greater force will be applied on each electron, and that will result in, first of all, greater attractive force. Second thing, one electron has been removed, so the repulsive force are also decreased, and hence it will contract and result in a smaller radii as compared to the neutral atom. Now, greater the negative charge on ion, larger is its radii. So, why are we saying so? So, this is the case for anion. So, whenever we are considering anion, so anion have always greater size than the parent nuclei. Again, the reasons are obvious. If you just analyze the reasons for positive one, you can easily get the reason for negative one, because when we add an electron, there is an increased repulsion, right? There are number of electrons is increased, so there is a increased repulsion. At the same time, what we see is that the effective force on each electron has been changed, or you can say it has been decreased, because the protons are same but the number of electron is greater. As a result of it, the force on each of them will be distributed on a greater number of electrons. Now, due to these two reasons, you will find a greater say anionic radii than the parent atom. Suppose we have these three type of atoms which are charged differently, but they are fundamentally same. So O minus, O2 minus. So we can see this is the trend for the atomic radii, so ionic radii. So as we are increasing the charge, we are increasing the radii. Now, for isoelectronic species which possess same number of electrons, so what are isoelectronic? The elements which say the species which have the same number of electrons are called as what? They're named as isoelectronic species. So for that case, ionic radii is inversely proportional to magnitude of nuclear charge. So greater is the nuclear charge, means the charge that is on the nucleus. So that greater will be the nuclear charge, smaller will be the ionic radii. Now let us try to summarize all of this. So first of all, we mentioned some earlier attempts. So there were various attempts like your Dmitry Mendeleev attempt, your Newland's octave attempt. So there were some notable attempts. So that includes Dovenier traits, Newland's laws of actives in 1864, Mendeleev periodic table in 1869. Now then we have the modern periodic law and the present form of periodic table. So according to the modern periodic law states that the properties of elements are periodic function of their atomic number and not weights. Again, this is very, very important point to remember. Okay, so every physical and chemical properties can be considered as the function of the atomic number and not atomic weights. Now, so for that reason, what are we doing? We are arranging the say elements in the terms of their atomic number and not the atomic weight. Next is classification of elements. So we know that they can be classified into various categories. First is metals, non-metals and metalloids. Depending upon their lustrous properties or their conductivity properties, we know that they can be metals, non-metals and metalloids. Second thing, we have seen that in the periodic table, we can divide them as groups and periods, right? What are groups? So you have seen it. So it is starting from 1 and going to 18. So this is the new way to do it. Initially it was subgroups like 1A, 2A and goes to 7A. But now it is going from 1 to 18. Okay. We talk about periods. There are 7 periods from 1 to 7. Okay. So this is the way. Again, we have the block system also divided. So S block, in which the last electron goes to S orbital. P block, the last electron goes to P orbital. D block, the last element goes to D orbital. And the F block, where the last element goes to F orbital. Now, S block and P block elements are collectively known as representative elements or main group elements. Now, D block elements are called as transition elements and F block are called inner transition elements. If we talk about the periodic trends, so several properties of element exhibit periodic trends across the table, like our atomic radii, which can be of 3 types: covalent radii, metallic radii and van der Waals radii. Okay, so thank you. This was all for today's class.